Ladies and gentlemen, we're going to be starting to talk about recursive functions, which are mentioned in section 510. If a function calls itself, that function is recursive. So we need to remember some fundamentals as well. A recursive function is made up of two fundamental parts in the order that I mentioned below. There must at least be one base case or a termination case, which checks a condition that will end recursion, which means in a base case, all we do is return or return a value, but we do not place a recursive call to ourselves. There may be multiple such conditions, but the thing is there has to be at least one. And number two, in the function, you need to have a recursive reduction step in which we solve part of the problem and delegate the rest of the solution to the recursive call. Again, there may be multiple of these, but there must at least be one such recursive reduction step. So let's consider counting down from some integer value n down to 0 using the following function signature. So we're going to call countdown n. So this thing is going to count down, let's say if n is 10, down to 9, 8, and so on until we go down to 0. And then when we go down to 0, it's going to say blast off. So how can we write such a function? Before we can do that, we need to make some observations. First is that we need to end the function when n value is equal to 0. And to count down, we're going to have to decrement n by 1. So let me actually add that little detail there. So we might write the function like this. So count down n. If n is equal to 0, we print blast off and we finish. Or we can actually put in a return statement. We don't need to. We will just do the same. We will do it implicitly, even if we don't put it in return. So return doesn't do anything here, so we just leave it aside. But if you wish, you can just put it in there. So let me just do it like this. Just to actually emphasize that that's what's going to happen. We're going to return from the function at that location. And then we can print as many right angle brackets as the value of n. So I'm using f strings, which you should have read about when we did the string formatting. It's very simple. We just do everything within the string instead of calling arguments from outside, with dot format and all that, which is also nice, but this is easier in many cases. So I'm just using it in some places for you to learn. So I have this character I'm printing n times, and then I'm just going to display n itself. And then I will be counting down. I will be calling countdown again with n minus 1, so one less. So if I come in with 10, I'm going to be calling 9, then 8, and all the way down. But I'm checking whether n is 0. Whenever n is 0, I'm actually printing blast off and then stopping. So let's run this. So we see that we had just gone down from 10 to 1, and then when the n value is 0, we just print it blast off. Well, let's just soup this up a little bit so that we can see this happening a little slower. So we're just going to slow down the printing of the messages by using time sleep. So I'm going to just make the system sleep for half a second, before I do the recursive step. So let's just see how that would happen. So we're running right now. So you'll see 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then blast. So we can actually slow it down some more. Let's say with 3/4 of a second. So you can just put in 1 for 1 second, 2 for 2 seconds, and so on. So so far so good. Well, I'm going to switch to the problem in the book, and that says we need to print a right angle triangle like this with individual symbols. You can use anything for these, given a side length. So initially, we're going to write a function that's going to do this iteratively. a little different from what the book does. So this discussion is actually quite a whole lot richer than the one in the book. And I'm going to be adding some other things that are not mentioned in the book that I find are essential. So it's going to be a much deeper discussion because I consider this really a critical part of programming, and we should get into it at this moment and then start keep going back to it um, throughout the semester. So I'll be printing this triangle. If I print this triangle with value 5, I'm going to be printing um, five a triangle with 5 symbols on the bottom, and also it will be 5 lines deep, as you see. So let's make some observations here. So first of all, we start from 1, or start from printing 1 symbol. Then we count and keep printing until we reach side length. So we finally come to 5, and then we print 5 things in the case of the example above. So we'll be printing as many symbols as the current count. We're going to start from 1, go until side length, including side length. So we can write a function like this. So I'm going to use an optional or a keyword argument, and I'm just not going to even bother with this one while I call the function, because I'm just going to set it to this block character. And so I'm just going to simply count for any in range side length, and I'll be printing the symbol as many symbols as n, but since we start n with 0, I'm just going to add 1. So I'm just duplicating the symbol as many times as n plus 1. So when we run this for 5, we just get what we need. So we could actually do range 1 to side length plus 1 and not have to do this plus 1 here. So we do the plus 1 here, so we don't have to do it like this. So just do this as an exercise on your own. I may ask you to do this as homework as well. So it's just a simple change. So now we're going to switch to writing this function using recursion. The same observations still apply, but the thing is, we're going to call our function with, we're going to name our function with the suffix r1 to indicate that this is a recursive version. But the API is still the same, except for the little name change. So let's make some of those observations again. Given the API we need to implement, we can only start from site length, because we're going to be given site length, so we need to start, we can start from it. We cannot use a loop, because recursion, cannot use loops. We end up essentially emulating loops by calling them ourselves. And then second observation is that we can count until 0. The function, better stop when site length reaches 0, because we're going to be calling site length -1 every time. And at each step, we will print as many symbols as the current site length value. So here we go. So first we check if site length is 0. If so, nothing to do. Then we print as many symbols as the site length, and then we call our function again recursively with site length -1. What happens when we run this? Well, we end up printing the triangle upside down, because initially I'm going to have site length equaling 5, so I'm going to print 5 things. Then I'm going to call the function again. I'm going to go back. My site length will be site length -1, so I'm going to display 4, then 3, then 2, then 1. Then once I go down to when site length is 1, I'm going to be calling print triangle with site length 0. So I go back and I stop, because the if statement will see that site length is 0, so I will just return. But oops, this is not what we really want. The triangle is upside down. It's an okay implementation, but it doesn't satisfy the requirements. So if we count down, we can only print the triangle starting from the base of the triangle and not the tip, so it ends up being upside down. So we need to rethink. So we need to get this image instead of the upside down image. So let's divide the problem up into two parts as far as the above example is concerned. Let's just imagine that we can print the first 4 lines of the triangle the right way up. And then the only thing we're going to have to do is just simply print the last line, which is the line with 5 symbols. Okay, again, we're just going to somehow imagine that we can print the first 4 lines magically or recursively, and then we're just going to be doing the last line on its own. So printing the triangle with the first 4 lines, and then we're going to be printing the last line with 5 symbols, or we can reformulate as a program. So print triangle R2, side length -1. So this will be this will mean that I'm going to be printing everything up to the the first 4, and then I can just finally do a usual print with symbol times side length, printing the bottom, just like we formulated here. This is also mentioned in the book, so I'm using the same logic. So let's give this a try. So I place the recursive call with side length -1. Hopefully this will draw us the first 4 lines, and then I will draw the last line. I'm going to get done, right? So let's just run. Well, it's still running. Whoops. You see. Well, we ran out of recursion depth, because actually, even though we have just done this exactly, we have not really done a recursive function, because where is the base case, which should go first, and where is the recursive reduction step that should go second? So do not mix the order of these two. They have to be exactly in that order. So we're gonna have to retry. So remember our observations. If the side length goes down to 0, we need to just simply return we have nothing to do. So I will call this the proper implementation. And else we're going to print the triangle side length -1. Again, we're just going to be passing the symbol. We need to pass the symbol in. And then we're going to be printing finally the last line. Okay. So when we print, oops, whoa, it works. Oops, in the sense that we got it right. Well, the big trick here is to place the recursive call before the solution to the part of the problem. Okay, so you see that unlike in many cases, we are actually doing the recursion first and then doing the solving the current, or part of the problem. Part of the problem is, in this case, drawing the last line for any side length value. But how does this work? Can we show that? Can you prove that, or can we understand the logic behind this? Well, we need to actually draw stack frames to demonstrate how this works, but let's go to our earlier example first, the countdown. But we're going to soup up this function as well, so that we can see what's really happening. So I'm just going to place an indent, and indent levels will go down as I keep calling, recursively, and they will reduce as I come back out. So you can see that I'm printing the end value, and I'm just I'm determining the indent string based upon my indent level. So I'm just going to be duplicating this string. So I'm just going to keep pushing things more and more to the right. And then I print a few other messages to tell us what's really happening. And at the end of these two, at the very end, before I return from the function, I just say returning from, maybe I should just do this uppercase. I'm going to return, and I'm telling you which particular countdown call I'm returning from. Okay, so I'm going to set A to 4 and then call countdown. So the thing to remember here is, well, let's just see what happens with this one. So you see, I'm starting with 4. I print 4 and I place a recursive call again to count down and with n equals 3. Then I print 3. I place a countdown to 2. I print 2. Place a countdown to 1. I print 1. Place a countdown to 0. When I come to 0, I reach the base case or the termination case, and I just print blast off, and that's all I do. I don't necessarily, but I did not put a return here because I want my execution to continue, because the if part will be done. I'm not going to do the else part, and I'm going to do this. And finally, I'm going to be returning from here. Even if I do this or not, it would be the same thing. But I don't want to put a return here because I want to come here so that you can tell once I finish, when we finish the recursive parts as well. So when I reach blast off, I'm not going to do the else part. I printed blast off, then I'm going to be returning. What am I returning from? I'm returning from n equals 0. Okay. So I forgot to put the n value here, so let's just do it like that so that we can see. Right? So when I return from this, I ended up returning to, as you can tell, to the context of countdown 1, because that's who called me. And then once I return there, where am I returning actually? I got called from countdown 1. So I got, so imagine it was n equals 1, so 1 minus 1 would be 0. So I call countdown 0, then I check for the n value, which would be 0, and then I would stop. Where do I return to? Where I was called from. So I come back to this location in the program when n was 1. So then I continue, and then finally I return. But before I return, I print returning from countdown 1. Same thing for 2, 3, 4, and I come all the way up. So functions do not return until we reach the base case. So you should remember that. So the way this works is that every time a function is called, the system creates a stack frame on top of the system memory stack and sets up the execution environment by creating and initializing the formal parameters and then creating everything else, including local variables. So let's see what happens with countdown 4. So I'm in the global environment. I'm ignoring the built-in scope here, so to make things easier. So I set A to 4, and I count down with A. So A is 4, so I'm calling countdown 4. So here's the stack frame, or actually this is the execution environment for countdown 4. N is equal to 4, I print 4, then I call countdown 3. So then I go into another function called countdown 3, where n is 3, I print 3, I can go down to call countdown 2. I go into another environment, this time for countdown 2, and then I print 2, then I call 1, and then I do the same things, and this time, finally from 1, I call 0. When I call countdown with n equals 0, n is equal to 0, so it's time to do a print blast off, and then I return from the function. This is the first return I actually execute. When I get out of this, I go back to the box of countdown 1, and then I finally return from there. Then I return back to the outside box, which is countdown 2 box, and I return from there, and I go all the way out. And finally, when I return to the global context, I essentially return from that, which actually ends up exiting from the program. So we can show these things as separate frames. Then we can do it as follows. So I have the global context here. So I set within the global context a to be 4, and I call countdown with a. So I end up calling countdown 4 here. I print 4 and I call countdown 3. This is the context for countdown 3. I print 3, I call countdown 2, I go down to 2, I print 2, I call countdown 1, I go down to 1, I print 1, I call countdown 0, and then when I call countdown 0, the if statement will actually print the blast off message, and I will be returning from the function. What will I return? Where I was called from. I go back this way now, and I go back to where I got called from, which is the context of n equals 1. Then finally I return from that one back to countdown 1. I countdown 2 to 3 to 4, and finally I return back to the global context from where I placed the initial call. So that's how this works. Now back to our example. Why did print triangle R2 called with side length 5 work? Well, here is a more elaborate drawing of what happens. I'm dividing things into 2 here because certain things are going to be here will be happening on the way down, and returning will be happening on the way back up. So I call from the global context print triangle R2 with 5. So side length is set to 5. So this is the context for print triangle R2 5. What's the first thing that happens? I call print triangle R2 with side length -1, which is 4. I don't do the printing yet because I have not yet returned from this call. So I make the call to print triangle R2 4. So side length is 4. Again, since side length is not 0, I call print triangle R2 3. Then from there I call print triangle R2 2, then 1, then 0. Now this is the actual call where side length is 1, so I'm placing the call to print triangle R2 0, and I go into the stack frame of print triangle R2 0. Side length is 0 here, so my if statement actually executes because the condition is true, and I just return from the function. So this is the stack frame I am in right now, and I'm returning from it. What am I returning to? I'm returning to where I got called from, which was print triangle R2 where side length was 1. Well, now I will do the second line in the code, which is printing the symbol. How many symbols will I print? I will print as many symbols as my side length. So symbol times 1, which is what the side length value is. So I just print this. And then there's nothing else I can do within this context of where side length equals 1. So I return again. I return to where this context was called from. Well, that's the one with side length equals 2. So again, I do the remaining part of the code because I got called from here, and now I return back there, which means I'm going to do the next thing right after that, which is printing. And I'm going to be printing 2 things and then returning. Then I'm going to be doing the same thing up here, printing 3 things and returning, printing 4 symbols and returning, printing finally 5 symbols and then returning from the function back to the global context. And in that case, there is nothing else that we need to do. So we are actually going to be exiting from the program. So if you look at the numbers that I put in, that's the order with which things will happen. Initially the call, then these 2 things, the setting of the variable, and then calling the recursive function. Same thing here all the way down. And then finally, we start returning. And when we return back to where we got called from, back to the previous contexts of the function calls. So 8, 9, 10, 11, 12, 13, 14. So in the 14th step, I'm done with the function I have already drawn, but you can see, since the first thing will be this thing, the first symbol, the 1 symbol, 2 symbols, 3 symbols, 4 symbols, and 5 symbols, I'll be printing the triangle right side up. So that's how actually that works. So take a look at this, make sure that you understand this really, really well. I've taken the time to draw this for you so that you can actually see exactly what's happening. Well, we need to note that there is yet another way to solve this problem. If we want to think in a way in the forward fashion, meaning we want to just count things down. But obviously, I mentioned before that if we cannot just uh, implement the counting down version the way we did it, but we can do this using an inner function. So we have print triangle R3 side length symbol, exactly the same parameters, but I'm going to be defining a function inside this function. So it's like I have an enclosed scope here, if you remember from our discussion about scopes. So I don't need to pass in the symbol and the side length because I would already know these, because these two are local variables within this entire function body. Even if it's an inner function, it doesn't matter. Still, these two things are accessible, so I don't have to pass them in. I can if I want to, but there is no need. So this n is the value that I'm going to be counting down. So how would I pull this off? So since I'm going to be counting down, I'm going to go from 5 to 4 to 4 to 3 to 2 to 1 and then 0, and if need be down to -1. So the way I'm going to print things, if I want to do the printing first and then do the calling of the function second, I want to change things. I need to change a few things. So let's see. We're going to be printing the symbols first. So I'm going to be printing, but I cannot just simply print n number of symbols or side length number of things, which would have been totally wrong. But instead, I'm just going to have to print side length minus n symbols. So initially, n will be 5. One moment here. So that would print 0 things. Maybe I'm just off by 1 here. So initially, I want to print 1. So how would it be, right? So if n is 4, I'm going to be printing 1. Okay. So initially, side length minus n obviously will be 0. So I'm going to be duplicating something with 0, so it's not going to print anything. And then I'm going to be calling n. I'm going to be calling this function recursively, print triangle inner r with n minus 1. So if I start with 5, then I'm going to call it with 4. So then side length will always be the same, so it will be 5. Then I will be doing side length minus 4. So 5 minus 4. The next time, n is going to go down to 3. So I'm going to be doing 5 minus 3. So I'm going to be printing 2. Then side length minus 2. Then I'm going to be printing 3. Then 4. Then finally 5. Okay. So the final value of n would be 0. So side length minus 0 would be 5. And then after that, I would be calling, so since n value would be 0, I'm going to be calling this value with -1. That's when I want to stop. Okay? But I don't like this idea that the first call is actually side length -1. Let me just try something really quickly here. Because if I have a value, let's just call it x, and I duplicate this 0 times, what am I getting? I'm just getting an empty string. So that I just don't want that it's an ugly thing. So let's just keep it there. So in the first time, actually, what I want to do is I want to make sure that I just print the first thing. So n has to be for the first time. Okay. So when I call this with side length, instead of that, I'm just going to call it with side length -1. Okay. So let me run this. It just still runs just fine. So I will be just going down. So I would be starting n from 4. Then I'm going to go down to 3, then 2, then 1, and then 0. I want to do this when n is 0. So when finally I'm going to be be doing n equals 1. Then I'm going to call this 1 minus 1, which would be 0. But I still want to go down and then execute this because I want 5 minus 0 to be 5 to be able to print the last line. Then finally, this thing is going to be going down to -1. That's why I cannot check if n is equal to 0, 0. I could have done that as well. I explained up here. But a cleaner thing would be just to go down to -1 and then return, because I want n0 to be processed right here, right on this line. Okay, so this is another way of pulling this off by just counting down, but I have to have a method with which I can remember what side length is without changing it. If I keep counting down, right, uh, it wouldn't work. And there is another uglier way of doing this thing, but I'm not going to show that to you. I'm going to cover that, but I'm not going to cover it with in the context of this solution, which would make no sense. That method makes sense in other contexts, but not in this one. So this is another way of doing this. And I wrote a bunch of things for you to read. These are all comments and doc strings. So this is to help you along. So you should just read everything and make sure you understand what's going on. So if putting the recursive call first didn't make a whole lot of sense, but I need you to understand that solution as well, because it's really elegant. And it's more elegant than this one. And you wanted to think more directly, meaning you just want to print first and then call the recursive function. This is the way you can pull this off. Okay. So I will ask you to draw the stack diagram of this thing, but you can just do it before you wait for me to ask you in the next homework probably. So that you prove to yourself why this worked, because after all we have recursive calls, every single function call, no matter whether it's recursive or not recursive, will cause a stack frame to be placed on top of the stack, and then the next call will place another stack frame, the next one will place another stack frame, and you have the n values and the n value to work with. And then every time there's something is going to be happening with respect to the print statement, and then you need to know exactly when the returns are happening. So you can place return or print statements elsewhere to inform yourself as to what's happening. The printing will be not happening as nicely because you would see the printout statements, but to study how this thing is working, you can place a print statement saying let's say like finally done, and you can say printing side length -1 symbols, but I will turn this into an F string. So we could do this like this. So you will see that it's just going to be printing things like this. But you can tell what's happening. There's something wrong here, so it's supposed to be -n. So it's a printing 1. Then 2, then 3, then 4, then 5. So we can tell why it's happening, but you also need to understand the stack diagrams. So I'm just going to comment these out and leave them for you to open up if you want to see what's happening. So this is it. Well, let's take a look at a function just to repeat something we did before. If I just simply call myself, you see, I'm calling with n, so I'm just calling myself recursively with n-1. Is this a proper recursive function? Well, I'm just simply going to place recursively 1 and see what happens here. It's running, you can tell from here, right? This means it's kernel is busy. Well, of course, maximum recursion depth exceeded. Remember what happens when we don't write proper recursive functions that do not have any end. We exhaust the recursion, the stack, we run out of memory, and it just doesn't run. So it just fails. So important thing to note, and this is the reason why I wanted to revisit this problem, is what resources do we really need to execute a function, actually, any function, recursive or otherwise? Well, to execute anything, we need two things: memory, which means general space, and we need time. and actually specifically CPU time. Without these two fundamental resources, we cannot do anything. So if we run out of any one of these, we simply cannot compute even though everything on paper works. So when you write infinitely recursive functions, Python will, kernel will be interrupted automatically, and your thing will not run. But we'll see some other problem with recursion in the next few sections. So we're going to look into the factorial function. You should know from math that factorial of 0 is 1, factorial of 1 is 1, and factorial of n is n times factorial of n minus 1, because factorial is n times n minus 1 times n minus 2 times all the way down to 1. So we can just separate the latter part, which starts from n minus 1, goes down to 1, as factorial of n minus 1. So we can define a factorial like this recursively, and we do so in math. So obviously factorial of 0, factorial of 1 are both base cases, because they don't require any recursion. They are not. So the left-hand side of the equation is not defined. Um, um, well, we define the right-hand side of the equation in terms of the left-hand side, as you see. You get factorial and factorial, recursion, or cyclically defined actually. So this is a cyclic definition, which means recursive. So we have, in the recursive portion, we have this n times factorial of n minus 1 part. Well, we need to know which part is which in the recursive reduction part. Well, n times part is solution to part of the problem, and n minus 1 is a delegation of the solution to the rest of the problem, or it's the solution to the rest of the problem. And in terms of factorial, we need to multiply these two to get the result to the current n value. So I think I don't have the factorials here. Might do it later on. Sorry, I got things mixed up a little bit. I'm gonna come back to this, I guess. But let me just do the factorial here as well. So we can write the factorial function as follows. If n is equal to 0 or n is equal to 1, we return 1, just like you see right here. Otherwise, I'm going to be returning n times factorial r of n minus 1. This is just a mathematical definition, nothing else. So factorial of 3 should be 6. Factorial of 5 should be 120. Actually, let's go with 4 first. 24, because it's 4 times 3 times 2 times 1, or actually it's 1 times 2 times 3 times 4, right? And so on. I can try a little higher values. Let's try 10. Comes back as this big value. I can try 20. I can try 30. The numbers are growing, and as you can tell, execution is slowing down. Let's try 50. See? Watch with 70 now. It took a little longer. Let's try factorial with 100. See? So it's taking more time, but we cannot see, how long the execution time is changing with increasing values of n. But this is all there is to it. Actually, we can change things, around a little bit. So let me drop a little note here. No, they're coming back almost quickly. Maybe I will just try another value. Let's try about 1,000. No, that came back pretty fine. It's a huge value, as you can tell. We can, keep going up, and we can try these things. So I'm going to jump to the Fibonacci function. The Fibonacci numbers are those that are the summations of the previous two Fibonacci values. So the base cases are Fibonacci 0, which is 0, Fibonacci 1, which is 1. Then Fibonacci 2 is 0 plus 1. So let me actually show you this. Let's see here. So Fibonacci series would be 0. Then 1. So 0 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34, and so on. Okay. So I give you a link to for you to read Fibonacci about Fibonacci numbers, and we can take a look at it actually, but I'm not going to take time. It's very interesting because there are some natural phenomena that actually follows this series. So this is what we have. So this is the mathematical definition. Again, the right-hand side has two calls though. So it's the cyclic definition. It's using Fibonacci again, and so we are defining Fibonacci in terms of Fibonacci. And we have two Fibonacci calls, and they are n minus 1 and then minus 2. So we can write this so if n is equal to 0 and equals to 1, we need to return not 1, but n, so that when n is equal to 0, I return 0, and n is equal to 1, I return 1. And the recursive step, or recursive reduction step, is Fibonacci n minus 1 plus Fibonacci n minus 2. So I have two calls. So this call is going to go out, it's going to have to come back, then I'm going to have to add that result to the result of the second call. This is going to have to come, go out, do everything it needs to do, and then come back. Well, we can write nice test functions to see, what's happening. So I devised the simple function like this. So I'm passing in the function and the n value. So I'm just going to target this to test my Fibonacci function. So I call the function here, and I get the result. I pick the function name using the underscore name underscore field of a function, and I print the name, the argument, and the result, and I return the result just in case somebody needs the result, just like in the regular call. So I'm just making a few calls here from n values from 0 until all the way to 5, just to make sure that I'm actually working out. So there is something wrong here because these are not the results that I'm supposed to get. So one moment. So if I call if 0, I get 0. I call it with 1, I get 1. I call it with 2, I get 1, which is wrong. There is something wrong here. Can you see what's wrong? You see this is live programming, and I'm just seeing if n is equal to 2. There is something wrong here. So let me not take your time, and I'm gonna just pause for a little while and then fix it and come back and tell you what's wrong with this. Well, we're back. There was actually nothing wrong. There was just something wrong in my thinking, so I just want to share that with you. Anyway, so I just fixed things up a little bit so that I put together a nicer table. So it was just my computation was wrong, but the function was just fine. So n values are listed from 0 until 9, right? So what did we say? The first two values are base cases. So let me just actually even do this. Let's just divide these two parts. Sorry. So these first two cases are base cases, and everything else is not. I think one more space here. Oh, it's uglier. It's okay. All right. So the actual first recursive call we're going to actually get something meaningful out is actually n Fibonacci n2. But even if we call it for these other two, we're going to get the base cases. So Fibonacci of 2 is the addition of the first two values, which is 0 and 1. So I get 1 for 2. Fibonacci of 3 is the addition of the previous Fibonacci values. So it's Fibonacci, so it's the value for Fibonacci 1 and Fibonacci 2, which are 1 and 1, so I get 2. Then Fibonacci 4 is 2 plus 1, 3. Fibonacci of 5 is 3 plus 2, 5. Fibonacci of 6 is 5 plus 3, 8. Fibonacci of 7 is 8 plus 5, 13. Fibonacci of 8 is 8 plus 13, 21. Fibonacci of 9 is Fibonacci of 8 plus Fibonacci of 7, which are 13 plus 21, which is 34, and so on. Okay. So when you look at the function, I put a couple of statements so that it prints base case and it prints the result after it actually executes the returns from the recursion, or actually it's double recursion because we have two recursive calls. We can execute this statement and do the addition only after we return from all calls to fib with n minus 1 and all calls to fib n minus 2. So we can only then do the addition once we have the actual values back and do get back a return value, print, and then finally return that value. So we can see that we get base cases. Then for 2 we should get 1 because it's 0 plus 1 obviously. Sorry that I confused myself. So 3 would be 1 plus 1, 2, and then so on. And you can see print messages. Okay. So back to the test function. So if we test all these things, we're going to get, actually, I'm just going to go the statements because then it's going to make everything look ugly. So let's run these again. So when I run the test functions, I just get all the values in, and then the last one will have its return value printed here, so there's no problem. But I just want to actually try higher values, but I want to Why do I have these things upside down? Because I was supposed to do this. So we can try higher values, as you will see. So let's just try, let's just click directly, Fibonacci of 10. Just immediately coming back. Let's try Fibonacci of 20. It's coming back. Let's try Fibonacci of 30. It's taking a little time, as you can tell. Let's try Fibonacci of 35. I'm doing this thing because I've experienced a little time. Like before, you see, we're just waiting. And you can tell if I run this thing, take a look at this side. This circle will be black, which means kernel is working, executing, and then it takes a few seconds before it comes back. So suddenly time, execution time has gone up. So let's just write a simple function to measure how long it takes to call these functions, and then do a graph to even understand much better about what's really happening. So it's a really simple thing. You import from time, and you just take the current time, call your function, and then take the next time, and then do the end time minus the start time, get the duration, return the duration. It's as simple as that. So if you measure the time for Fibonacci 10, so I'm just passing in the function, and I'm passing in the arguments. So I'm just calling the function here. I'm not returning the value of the function because I just need to return duration, how long it took in terms of seconds. So Fibonacci of 10, Fibonacci of 20, then 30, 35. Oh, 35 is working still. Oh, it's back. See, it took almost 8.5 seconds. 36 will take a little longer. Still working, as you can tell from here. It's back. Let's just take it up to 37. We're waiting a little longer. You see, it went to 5.5 seconds, roughly. Then it went to 8.5 seconds. So let's just collect some timing data from using measure time. So what I did is, some of these things you may not know, but I just generated a range from 1 to 21. So I want to get values from 1 to, I could even do 0. So because I have Fibonacci 0 anyway. So let's just do it like that. And then I just tagged along these higher values, but I don't want to take them higher. You can try Fibonacci 50 if you want to wait a long time. You may not even have enough time to wait. So I just added these things at the end. So these are going to be my n values, and now I'm going to measure. So we're going to wait a little bit here, but just bear with me. So I'm calling Fibonacci of n with all these values that I'm going to get from 0 until 38. But I'm going to jump from 20 all the way to 30 because I don't want to try all the ones in between. Actually, I could have done this altogether, but I would just be waiting a little bit more. But anyway, up to 30 is fine, so I can actually just simply do this all the way until 39, so I get 38. So if you wanted to see the n values, I was just going to show it to you, but there is no need for this even. So what I can do is I just place this right here, range 39. So don't even need this. Okay, I'm gonna keep. Sorry. But I'm gonna have to go back. I'm gonna need the n values because I'm gonna be plotting. So sorry about that. So I want to turn this into a list so that I can have individual values. So 39. So I'm just going to go back and values here. So I'm doing list comprehension, which I'm going to show you guys when you do lists, but it's very simple. You just do the for loop here. and for each n, you will create this element and add to the list. Okay, so here we go, we're running now. So we can see from here, it's going to run. It's going to wait, we're going to wait a little bit. And you can tell from my machine's CPU fan that it's working really hard. But it's going to come back in just a little while, just a little. Still waiting. Finally done. So I can display the t values I get. I get really low values, and then they start going up and up and up. But I cannot tell much from the numbers themselves. So I just do this. Just shown in books. I just want you to understand this much. It's very simple to use. So we import pyplot from matplotlib is plt, so we don't have to write this whole big name anyway. And then we have plot x values versus y values, and so we have n versus t. And then I just put labels in and I display the graph. So here is our graph. So since I used all the values, the graph looks nicer than the one that I did originally when I was preparing these notes. But anyway, much better like this. Well, we can tell a whole lot from this graph. So suddenly, within a few values, the execution time is just zipping all the way up. So while we didn't have to wait any time for n equals 0, for 36, 37, we have to wait 12 seconds, 14 seconds, 13 seconds, thereabouts. Okay, just went up, way up. So we got a problem, Houston. The function is executing just fine in terms of being, the implementation being sound. So I need to change this stuff here. It's correct. The implementation is fine. But what's wrong? Well, you remember what happens every time you place a function call. In the Fibonacci function, we have two function calls that are recursively being called. So each of these is going to build a stack, and it's going to be expensive to run this with high values of n. So we can take a look at recursion trees here. So the summary of this thing is, when you look at this graph, this graph is exponentially growing. So execution time is exponentially growing with respect to the n value. So we would have to wait quite a bit to do n equals 40 on my machine. Maybe your machine will not even take 35, because it has to be somewhat fast and somewhat with loaded memory. So you may not even be able to run this as high as this, but at least I can show you on my machine, that execution is going to keep going up smoothly like this. It's going to just shoot up like this. So so we can say the following: the recursive implementation of the Fibonacci function is simply not practical. Okay, so I'll skip this section. You guys can read this about type checking. Well, let's go back to iteration or looping. We must distinguish between recursive programming and recursive execution. Just because a program is in some programming language has been written in the recursive format does not necessarily mean that the program will also execute recursively, meaning it will build stack with every call, every function call. There are some programming languages that recursively, that allow recursively written programs to execute iteratively without building stack. So you reserve the elegancy of being able to write recursively, but yet you take advantage of the programming language's ability to run things iteratively, which is wonderful. But Python is not one of these languages. So if you write something recursively, it will execute recursively. But some other languages, such as Scheme, allow for what's called tailed recursion. So if you place your recursive call at the very end of your function, then it will not build stack. But unfortunately, Python doesn't allow for tailed recursive calls, but we can at least show how we would implement the factorial function to get this going, or to actually enable a tailed recursive execution. Nevertheless, the implementation I'm just going to show you is tailed recursive, but it's just going to be still running recursively as before. And the trick is that we will be carrying along the result in our parameter list. So we're going to put in an additional parameter called result. Initially, since we're multiplying, initially this result will be 1, but we're just going to compound onto it by just multiplying. So we're going to be using n just to count essentially. So when n is equal to 0, we're going to be returning the final result that was compounded into the result parameter. So any other time when n is not equal to 0, again we are doing factorial, not Fibonacci. So we're going to be taking n down by 1, but we're going to be multiplying n with the current result, or the result that came in. So initially this would be 1, so I would be multiplying the result with what? With n. What's the initial value of n? 5. Then my result will go in as 5, and then it would get multiplied by 4, then 3, then 2, then by 1. So with all these print statements, this is how this factorial of 5 would be running. So let me just say computation of factorial of 5. So we have case n equals 5. Actually, let me just do it like this. So factorial tr would be called like this from here. It would be called with n minus 1, which would be 4. Then the result will be 5 times 1. Right? These are exactly what would be called, what the value this function would be called with. Then this would call factorial of 4. Well, within factorial of 4, we're going to place a call to factorial of 3, but we're going to be compounding our result. The result was coming in as 5, and our current value is 4, so we're going to compound the result as 4 times 5. Then we go down to factorial of 3. So n is equal to 3. I'm going to place a call to factorial of 2, but I'm going to be computing my result as 3, the current value of n, times what came in from the function call, which would be 20, the previous result, 4 times 5. And then I go all the way down, and at the end, I have factorial of 1. And then, so my result would be 1 times what would be coming in, 2 times 60, which would be 120. And I'm going to be calling factorial of 0 with this result in. So when the if statement sees that n is equal to 0, it's going to return 120. So then I would be returning 120 at the end. So I could actually show it like this as well with the indentation. So 5, 1, 4, 5, 320, 260, 120. And then I would be returning 120, 120, 120 all the way back. This is very critical. Even though I'm returning it here when n is equal to 0, I'm returning it to the context of when n is 1. Then that would return to the context of n is equal to 2, 3, 4, and 5. Okay. So that's how this thing would work. Again, I need to drop in a line here. Exercise. Draw the stack diagram for the above case, of course, showing everything explicitly. So iteratively means that execution happens within a single stack frame. in the function that execution happens to be happening. Well, can we implement the Fibonacci function using iteration? Sure we can. But before this, let's ask the question of, can you do the factorial? I think I have it down below here, but my notes are a little bit... one moment. There's another discussion here that I'm going to let you guys take a look at later on. Yeah, so actually I should take this up. So the question is, can we implement an iterative version of the factorial function? Sure we can. So this is the function. So we're going to run it again, but anyway, let's just run it. So remember, the factorial of n is factorial of n times n minus 1 times n times 2, and so on all the way down to 3 times 2 times 1. So the second latter portion is actually nothing but factorial of n minus 1. So I can define factorial in terms of itself, getting a cyclic or a recursive definition. So here is the iterative version, which means looping. This is a function. When it gets called, it's only staying within the same function, right? The execution is not going anywhere else, which because I'm not calling any other functions, so I'm going to be executing within a single stack frame that will be created to execute this function called factorial I for iterative. So I'm going to just be running I in the range 1 to n plus 1. I'm just going to multiply this return value with I. So I'm just multiplying 1 times 2 times 3 times 4 times 5 times 5 to get factorial of 5, right? Well, we can also use the reduction or reduce function from the functools in Python, generate the values again, but then we reduce this range of values with multiplication. So I'm going to be multiplying 1 with 2, putting it back, and then multiplying 2 with 3, and then getting 6 and putting it back, and so on. So I'll do the reduce function in more detail later on, but I can just do it like this also. So actually I explained here, so all right, so let's just go through this. So let's just say I want to do it for I want to do factorial for 5, so I'll have values 1 2 3 4 5, as you can tell from this range expression, because I'm going from 1 until n plus 1, so I'm going to be including n, which is 5. So the reduction will happen like this. I initially start with this thing, so I take the first two, compute the multiplication, which I indicated here, because I'm going to be reducing by multiplication. I'm going to create that value or compute that value, put it back here. Then I'm going to take the first two values, multiply those two, put the value back in. Then I'm going to multiply the first two values, get the value, put it back in. I'm going to multiply the first two values, I'm going to multiply them. Then finally I'm done, so I just return the value, which is 120. So why would we be always preferring an iterative version? Because it's all about space and time. Since we're not going to take the time to prepare every single stack frame, because that's what it is anyway. That's the overhead that we need to incur when we call one function from another function recursively. So it's going to take less time to execute an iterative function because it only uses a single stack frame and it only just runs within that frame without having to call other functions. So implementing recursive calls will cost us in terms of space and time. So when the depth of the recursion is really high, Python will simply quit, as we have demonstrated a few times before. So but there is no need for any iterative version to ever quit. Recursive function is going and going and going, but it will fail with the maximum recursion depth. But here it's 10,000. We got failure with the recursive function -r, right? So far it was just working. I called the recursive versions, working. Well, failed with 10,000. Right? Well, iterative version, no problem. It's a long value, but it's no problem. So I'm going to close the output. So we have in the math library the factorial function, so we can actually use that if we want to. So again, you can tell that there would be an iterative implementation, not a recursive one. Well, can we implement the Fibonacci function using looping or using iteration? Sure, we can. This uses lists, so I'm just gonna simply describe it to you. So when you can refer back when we do the list, so we start with an empty list. The first two values, the base cases would be 0 and 1, so A would be 0, B would be 1. This is tuple assignment, which we have done before. So as long as A is less than n, we're just going to be doing the loop. We're going to add to the series the value of A. So A will start from 0, and then we'll set A to be B and B to be A plus B, right? To generate the Fibonacci values. We can maybe tell about this if we go back to the original table that I had, if I can find it right here. So this is A, this is B, right? So A and B values would be 0 and 1 initially. Then I say my A should be my new my B value, which was 1, and I set my B value to A plus 1, which is in this case would be 1. So I'm actually just moving my window by 1. So my window is here. I moved by 1 position, so I have 1 and 1. Then I have 1 and 2. Then I have 2 and 3. Then I have 3 and 5. Okay, it's going to go like this with this other implementation. So I can ask you to trace this function. Instead of just, let's say returning in a series, like we could just simply print things out, so I wouldn't have to use a list to do this, but I would just be returning, I would just simply be printing the series if you want to do it that way. But appending will just simply add to the end of the list. So we start empty, we put A, then after that we put B, then C, then D, and so on. So we can see that Fibonacci series 1000 here anyway. So this is actually not going to do Fibonacci of 1000. It will do Fibonacci until we reach the value of 1000. Because we're not printing the the end values, but you can tell from the length of this thing what Fibonacci this is. So we could do the countdown also recursively, as long as n is should have been, yeah. So as long as n is less than or equal to 0, we print, and we decrement n by 1. Actually, this should have been as long as like this, because we don't have any tests here. So let me just do a test here. So you see, it will just work. Let me just leave it like that. So I count down here as well. So as long as n is larger or equal to 0, I print, and then I decrement n. Once n becomes -1, this condition will not work. Then I'm going to be printing last of and then exiting from the function. So in the recursive version, Python would have to make a function call, the recursive call that is, for every n value. We know that calling function is costly in the sense that there is extra overhead that needs to be done in order to enable a function to run within a stack frame, preparation of the creation of the stack frame, preparation of the stack frame, and copying all the necessary values into the stack frame, creating all those local variables and such. So these things take obviously space and time. So function calls compared to looping is always costlier, no matter whether it's a regular function call or a recursive function call. But of course, if we are calling a function that calls another function that calls another function, we know that we're going to return, so that's not a big thing. The problem is when we have many function calls to do. So we haven't shown you what happens with the Fibonacci series, but you can take a look at the graphs that I think I had the link to, so you can see the call graph to see how it actually spreads out and generates so many calls. And it's that exponential growth of the call tree that ends up making the execution grow exponentially with respect to any in terms of Fibonacci. Something similar happens to the factorial function, but since there is only a single recursive call, it will take a little longer to get there. So with this countdown, under normal circumstances, if we wrote a recursive call, we would actually be making 6 function calls. But with the iterative version, there's just one that we have to do. So that's the critical part here. So we have other ways we can actually do the countdowns. So you can take a look at these. So no big deals here. So let me see if I have anything else to add. You guys can read these other notes that I have. I'm going to remove these. So we have this business of the break statement. Just to remind you that break statement will get you out of the closest loop or the loop that you are closest to. So I have devised this example for you to go through. When we break out of this, we break out of only the while loop here, not this one, because we have a while loop inside another while loop. So this is an elaborate example actually to teach you more about this break statement. So take a look at it, please. So this will just get you out of this while loop, and then we have the complement of break, which is continue, and continue always takes you back to the beginning of the loop. Okay. So again, that's going to happen even if, when we have 2 loops, when we have a continue inside the inner loop, it will take you to the condition of the or the top of the closest loop to you. So when we say continue, we go here. If we had another while loop, it would have happened the way I just said. So you can tell actually what happens with this one. We're just going to not do the remaining parts here. We're just going to go back to the beginning. From here, back to the beginning. That's what continue does. So we have an interesting thing. We had done this in class, I believe, but I forget now. Computation of the square root using Newton's method. So we had an initial estimate of x, which is 10, and we defined an epsilon, an error margin that we're going to use to stop the infinite loop. So we have while true, this will never stop unless we break out of it, as you see here. And I'm just going to compute how many steps also it takes to compute a value. So this is the formula for the Newton's method. So we need to, computes the next estimate of square root of a. We put it into y, and the previous estimate was x. Initially we start with a random value, it doesn't matter what. So I just put in 10, you can put in anything you want. It doesn't really matter what it is. That's how the technique works. So when I compare the last two values, the current one and the last one I had, if the absolute value of the difference of these two is less than epsilon, it means I have achieved enough precision, so I'll break out of this loop. And when I break out of this loop, I'm going to be returning y, the last estimate I have computed for square root of a, and I'm going to return the number of steps. So let's just compute square root of 9. Again, well, one point I want to make. All these values are floating point values. I never want to do equal. So I never want to check equal. So that's why I just check, like I told you guys in class, we compute the difference between the current minus the last value of the estimate, and we check to make sure that this is below a given error margin, which we stored in epsilon. If so, we just break out of the loop, and you leave, or you can just return y. I want to return multiple things here. I could have returned from here, but I just want to show you how the break works. So I just break out of the loop, return at the end of the function. So you can tell the current estimate starts at 10. Then I go down all the way, and then I just come really close to the 3. So in 7 steps, I return 3. I want to compute the square root of 22.09, because actually that's 4 point, square root of 4.7. And I just take 7 steps there as well. Let's try, so I get something really close. See, I have 2209, but when it's at the my result square root of 22.09 is 4.7, but if I take square root of this value, I get something 0 all the way, and then 3. So it's really close, really close, and it's below. This result actually satisfies my epsilon requirement. So square root of 144, it takes 5 steps. It doesn't mean that the value is large, it's going to take more steps. It doesn't mean that at all. So here I just want to start with another different estimate. But let's actually do that for 144. I'm going to start with the estimate 357. What the hell? So you will see here what's going to happen. So I go from, so then the next estimate becomes 178, then 89. Actually, am I printing X or am I printing Y? One moment here. So I come in with the next estimate. Okay, so I then compute the one after that, which is Y. Okay, and then I switch around. So I make the last Y I computed my next X, or the next estimate. So you see, I just go down all the way, and then my estimates come closer and closer to the actual value, then finally I'm done. So I can do a few more examples here. So 1453 was my answer anyway. So I just get it after 9 steps. I can change this initial estimate to something crazy, and then it will just, go all the way down quickly to the actual value, and then I'll get I'll get the same result, but after 18 steps. Okay. So I'm going to conclude this discussion on recursion. I just told you guys a little bit more, but it's a deep and extensive discussion. So you should read this notebook really carefully. And I'm going to ask you guys some of the exercises I mentioned in here. I think it turned out to be pretty detailed, and I wanted to show you guys what happens with execution of graphs. So you can do all these things. I just wanted to show you all this so that you can tell all you can do with programming to analyze data, to analyze all kinds of phenomena, to analyze how functions run, or anything else you are interested in knowing and finding more about and visualizing. So you can do all these things all with programming. Okay, so I'll stop here, and then I'll see you in the next chapter, I believe. Now I forget what it is, but I think it might be about lists. But anyway, those, I think, once you have all these 5 chapters done really well, chapters about lists, tuples, will be a whole lot easier, because these are more difficult subjects than dealing with lists, because after all, lists are really very simple to use. So there is not much going on with them, but they're very critical and they're very useful, as we'll see. But it's just mechanical anyway. But understanding recursion, understanding function calls, understanding stack frames, understanding random value generation, understanding what happens with all these things is actually quite critical. So you need to study these initial chapters really well, because we're moving along and we're doing a lot of things. So you need to be up with homeworks and labs and your reading. And as I told you guys, in writing, you should be picking up some other books I have suggested for you. Don't go anywhere else. Don't look for other books unless you check with me. Don't waste your time, watching one video after another video. I want you to watch my videos while doing what I do. Like, do in parallel, pick up the corresponding notebook and run things that I have done. And you may pause, you may do your own additional things, save things aside, and keep going with the video. Okay. But other than that, you may be spending a lot of time looking at somebody else's videos. There may be some excellent videos, but the reason why I don't want you to spend a lot of time on videos, except for this one, is that you should be engaging your mind doing your own studying, which means you should be doing your own reading and you should be doing your own practicing. So at least do the things I ask you to do. Then if you want to do additional things and watch other videos, look into other things, sure, do that. But you need to do the bare minimum, which is studying from the book, doing all the homeworks, doing all the labs to the best of your abilities. Okay, so I hope you follow this recipe, because it's going to get you success, not because I'm teaching the course, it's just the way it is in general. So I hope you guys do well in these hard times, because now you're studying on your own. Yeah, you don't have me in class to ask me questions, but you can of course ask me questions anytime over Facebook or through email. And I'm not doing interactive sessions because it wouldn't really all that practical, and I don't know whether I would be able to gather all of you guys. And I want to do it this way so that my videos are are available from beginning until end without additional things in between, because they're already taking quite a bit of time by themselves. So if you have additional questions, you can actually send me your questions if there is a need for me to answer with a video. If there is some extensive subject that I somehow missed, or something like that, I can just prepare yet another video for you, or maybe prepare a separate notebook, for you to read and practice on. Okay, well, we'll meet again in the next video. So take care and work real hard.